All right, welcome back to the stream. We are live again. This will be diving back into this kind of weird granular synthesizer project that I've been doing for a few streams now. This uses a somewhat CPU and memory intense pre-processing step to chew through a bunch of audio and generate a database of grain information. Mostly the pitch, although, maybe we might include other features at some point. Right now my focus is to sort on kind of a two-dimensional grid and have a synthesizer based on just playing back grains from a fairly large database with fast random access. This was kind of inspired by noticing how the really annoying TikTok text-to-speech voice has this extremely wide pitch range, and it's also very consistent. So it made me think that you could probably get it to sing or something, or use it as an instrument, at least by just copying and pasting grains of audio. So that's kind of what I'm doing here. I'm trying it on other source material also. That's part of what I'm going to get into here. Tuco just came back. Tuco, where do you want to be? Does he want to be right there? Maybe he does want to just be right there. He's giving me distinct vibes that he is not settled in yet. Maybe that's Tuco's spot for now. Oh? Tuco, are we still doing this? It's difficult to schedule my streaming around Tuco's moods, right? All right, is this gonna be stable? Okay, I've got this kind of low quality to-do list here with some things to work on. So I've got a bunch of additional input files now. I did actually end up, between streams, substantially rewriting the tool that generates these grain databases. To go. You can climb on stuff. To go. Are you trying to sit right between my keyboards, honey? Yeah, so I think as of the last stream, it was somewhat annoying that the tools for building these grain databases were even slower and more resource intensive than they really needed to be. It's not going to be a fast process, but my approach was to try to split it up into these two pieces so that I would have this. Oh, what is he doing? I don't think anything important has focus. Oh, he pressed numlock. Good job, Tuco. Gosh. Okay, we're just doing this now. Anyway, I was trying to separate the pre-processing steps into these two phases that I ended up calling scanning and packing. So when you're scanning, you're really just ingesting a bunch of audio files. So it converts, it decompresses whatever you've got. So if they're MP3 files, it converts them to wave. It converts everything to mono, floating point, because right now I'm not handling stereo inputs. The input formats are, I'm still kind of tentatively trying to keep things flexible, but there are still some places where it's making assumptions that are, they're not assumptions even, but I've got defaults that are really tuned to what the TikTok data set I have looks like. So it's supposed to support arbitrary sample rates, and I would like it to support stereo, but right now it's kind of focusing on mono and 24 kilohertz, because that's what the TikTok files are in. So I've got one thing that loads those into memory and does a bunch of pitch detection, writes out the pitch detection results, just generally using a lot of memory for this whole process. And that's the slow piece. That gives you kind of a variable amount of output depending on how many of these highly voiced grains or frames of audio that it found that it's turning into grains. So it just writes out everything it finds, and then there's a separate step where you kind of filter through what that tool found and figure out what you want to keep. And so my intention was to have a separate step that you can run with different parameters fairly quickly and just try out different things and see what sounds good or see what generates what size file. So that's this packing step. That's what was unnecessarily tedious last time, and now it's much better. So I've got a bunch of output files. They're in this format, which the plugin here does have support for. It's basically just a zip file with a JSON index and a binary array of grain locations, and then a FLAC file that has the actual audio all inside of a zip container. And so that's mostly working fine. It's just that it completely breaks for zip files that are larger than 2 gigabytes for some reason right now. Theoretically, even 32-bit zip files should be able to deal with up to 4 gigabytes. But yeah, I think if we go above 2 gigs right now, the zip file support and the FLAC support in Juice both have problems. So I haven't really gotten to the bottom of what's up with the FLAC support. That was a problem even before I added the zip container. libflac definitely supports large files. So basically the TLDR at this point is that I have something that kind of works, but I'm hitting various bugs in the convenient but kind of sparse wrappers that Juice provides for these things. And so I'm going to have to start swapping out Juice components with something a little lower level and figuring out a strategy for that. So I was thinking about the zip side of this. I just need to read zip64 files and also regular zip files. And I need support for deflate, compression, and uncompressed files. I need to be able to seek and uncompressed files. Basically, I need fast, pretty transparent access to one giant uncompressed file, the FLAC file. And then I also need to decompress a couple of smaller files into memory, which is the JSON index and the binary index. There's a question in chat about the price of RAM. It's been a while since I bought more RAM. The workstation I've been doing all this stuff on has 64 gigs, but I bought this hardware a while ago. There's a bunch of stuff that's been chewing up memory, but luckily it's all stuff that's fairly compatible with swapping to SSD, so I've been doing that. I've got a couple of 1 terabyte NVMe disks on here, and so I made a swap partition on there. That's how I've been dealing with this. Yeah, that's why on this machine, I think I've actually got like 300 gigs of swap space configured still. I don't think I actually currently need that though. So these tools will have to store all the audio that they're processing at once in RAM. So for the scan side, that's each input file multiplied by the size of, however much larger the pitch detection buffers are than the actual input, which is several, plus the size of just regular floating point buffers for all the combined audio. That's the part where I'm just like writing it to memory once and it can just live in swap space if it needs to. That'll easily just chew through, 100 gigs of swap space if you need, but I think it'd be fine with only needing a few gigs of actual RAM. And then the packing tool, since I rewrote it, actually needs very little memory. It's doing everything just like order of n using sorted. Well, so I guess it's doing some sorts that require loading the whole index into RAM and then doing some like order of n log n sorts or whatever it's doing. But then once it's actually got the index sorted, it's accessing the audio data just order of n, so that's not too bad. It's just that right now I'm dealing with source data for that step that's in numeric Python's NPZ format, which I was hoping to memory map, but they don't actually support memory mapping. It's not documented really, but the load method in numeric Python or NumPy just ignores the memory mapping parameter when it's in a zip file. Which is not that surprising. If it was doing memory mapping, they would need to be sure the zip had some kind of alignment guarantees. But considering they asked for a memory mapping mode in the API, I was kind of hoping that they actually went to the trouble of implementing that correctly, but nope. So it'll actually just use lots of RAM and copy the entire thing into memory. But that would be fixable if we used a different intermediate format than the NPZ, but I don't know that I care enough to re-implement that. Tuco is very round. I mean, the kind of data sets that I'm dealing with so far are up to like 30 gigabytes or so. So that, like, if it was staying in these nice 16-bit integers, that would fit in RAM easily. But it's immediately getting blown up into floating point, and then several additional arrays are getting created. And so, if I was really intending to, well, so there are a couple of different parts here, right? There's the total audio, which would be easy to just stream to disk. The only reason it ever gets loaded into memory at once is that I'm, for convenience sake, storing it in a single big numeric array. But then the part that would actually take some effort to rewrite is that right now I'm running this pitch detector on fairly large chunks of audio at once, because I want it to at least be something that begins and ends with silence. So I'm not doing any further splitting of the input files to the scanning step right now. So for the TikTok data set, those are like 30 seconds each, which is a little big, but not that big. We can load those into RAM and just make these giant arrays. I've been trying to process some other files though, which get really ridiculous. Like if I try to give it like pieces, like chapters of an audiobook, or like an hour of radio recording or something, then it will just quickly use hundreds of gigabytes of swap space. So that's something where if I was going to do files like that more regularly, I would definitely want a way to split those up. Could just do like fixed chunks, although it might be smarter to actually look for silences in the input and then split it up there so that I can run the pitch detector on these continuous chunks, because it has a probabilistic element that tries to smooth out changes over time. So I haven't looked at the algorithm closely though. Maybe it's already doing some windowing internally and we could just replicate that on the file input stage. Anyway, the whole pre-processing tool that I've been blabbering about is still like less than 500 lines of code total, so it's not that complicated. It's mostly just leaning on existing audio processing libraries. Can I still use my computer, or is that fraught right now? Okay, so that's just running in the background. That'll be fine. Oh, honey. This boy. Uh-huh. Oh, this cat. How much can I type without bothering Tuco? None. I can type none without bothering Tuco.
Alle dem Überseeschuld zu schütteln, Ölhahn zusammenzuleben her. Ringsum hervor fortzulaufen mit betrifft mit herumzuschlagen, hineinzukommen weggeredet.
Diffuses repining stability and congenitally jabbed mythic spools lucine comprehension large separator bullying.
Fault finder none in for your potpourris thyroidal monotonously intimidate zeros overbook murals pura pittance doing messmate orderlies flavors culminations overcompensation nationalization
Neuralizer dispute slides interlineage non-controversial seried abusing foundlings remagazes overconfidence unaware antiseptically
Weise allezeit sicherlich deinesgleichen leihweise woran
yeah, see, this one's only a little over 2 gigabytes, and this one hits one of the 64-bit problems. So we could load one of these smaller files. At least it shut up for the moment. It's fun that the file browser here recognizes that they're zip archives, because it's not looking at the extension, it's looking at magic numbers. Oh, honey, how is that comfortable? Round. It's time to just hang out with Tuke for a sec. you want me to move this, or do you want to lay on it more? Kitty. Yeah, Tuku's been eating a lot more than he was last year. Complaining a lot less about food, you know, he seems to be having a pretty good time. He seems comfy. Whoa. Oh. Oh, what even has keyboard focus now? Baby. Do I have any other objects you would enjoy laying on as much as the keyboard? Tuko, do you want this? Can we swap you a keyboard for a glasses case? I don't know if you actually want that, do you? I'm sorry, that was a ruse to take the keyboard. I do actually think this might be the softest thing I have handy. But, no, he specifically wants to lay on the keyboard.
In 2022, Republicans are like
make
An arrangement that will be seen.
Is being felt by
And in political debates, that leads to
because his government did not do enough on climate.
Da, unser und mal Herren achten achten und wieder mal 11-mal unterlässt uneinander gebüngst. Übelkeit eben dahin gegen deinesgleichen schwappt seit dem Ölproduzenten geschlichen, worauf X und sie
Synth.
All right, so yeah, this is maybe one of the more well-behaved examples. So this is more like what I was seeing when I first started feeding it just the TikTok voice. It's got a pretty wide range. If I throw in a couple of different voices, then I get a pretty nice variety in the different bits of the spectrum they cover, which is what you're seeing in this plot. And the volume is pretty uniform. There's a little bit of difference between the different TikTok voices, but they're all fairly uniform throughout. So, you know, pretty easy data set to deal with. But then the other ones are a bit more of a mess. Like the speak and spell is uniformly extremely loud. And then the radio is, you know, pretty uniform audio quality, but the volume is kind of all over the place and it has a lot of different speakers and pitches. Kind of similar story between the radio and these audiobooks. Although the audiobooks have an interesting spectrum plot already.
leaves the night, thou that it may
All one
Is burning as doth the flaming manifest to thee. But the hide that makes us servants prompts
God, I need a
to
better
the
knob
council
for
which
that.
controls the world.
For which no
pleasure thee to say, I was in them. Thus wheeling round did everyone his visage direct.
A crowd
This is the Mozilla Common Voice dataset.
The
Or
Austrian
part of
mil-
it. I don't think yeah, I wanted to run more of it, but that's still in my queue of things that will need a big chunk of CPU time to finish. This is just a small subset of the Common Voice data. Mostly you can just see how it's much denser in the middle of that spectrum. It's got a nice kind of smooth bell curve looking distribution. It doesn't really have much structure as far as the brightness axis here, the position in the file. It's because it's just sort of a random collection of small clips that have been shuffled, and it doesn't have any like sorting by speaker or anything like that. Whereas the audiobooks had structure by chapter, and the TikTok voices were sorted by voice. Anyway, this is like largely working. I was thinking about how to do the next steps in the like the grain storage layer, which, you know, I'm always like trying to think about how to fix the existing like known problems, because obviously the 64-bit issues are a problem that I need to fix. And I'm also trying to look ahead to the next couple of steps and figure out whether the architecture is still heading in a plausibly okay direction or not. Oh, to go. So there's kind of an unresolved question that in my mind for the design on how do I do volume normalization. I mean, right now what I'm playing is not normalized at all. Like, it's just seeking around in the file and playing what's there. But if there was, if I was trying to implement the same algorithm my prototype in the Jupyter notebook was using, that had all the data already available, it would, and like it wasn't trying to be real time. It could be as slow as it wanted. So it was actually just normalizing the RMS power from every single grain. Seemed like a thorough place to start. The more I'm thinking about it, though, the more I actually think I do like that approach, and I might want to try to do that in real time. And I was thinking about some maybe ways to do that with pre-computed data, but I don't even know if that's worth it. The thing that really, I think, seals the deal here is that I want to do the normalization after windowing so that I'm kind of picking a constant amount of energy for the portion of the grain that I'm actually using to deliver. And given the kind of variability I want to have in the windowing function, anytime you change the window function, that will also change, like it'll change the gain, so it'll end up changing the end, like the effective value of every single sample you're dealing with there. So I think I need to read the entire grain's worth of data kind of as soon as the grain starts to play, and just keep that in a cache. Use that opportunity to scale the gain of the whole thing and to figure out the window. Kind of figuring out in the design, like where to put the caches, like where do I want to store the data. Juice already has an approach for that, for buffering audio, which I was trying to evaluate. I already ran into some kind of insurmountable performance issues with that, though. It's really not intended for storing large amounts of discontiguous audio in memory. It's kind of more intended for just like reading ahead in just a regular streamed piece of audio that you're maybe seeking around a little bit, because it stores just like a list of 32 kilosample cached blocks that it just like rewrites the entire list every time anything about it changes. It's really not intended to be at all efficient for this kind of use case, at least. So I don't think I can use the thing that's built into Juice. It already was chewing up lots of CPU and providing no benefit that I could notice. The performance isn't that bad just in this test when I'm reading data directly from the FLAC file, which is what's currently going on. So in my real-time audio thread, I'm reading data from what's potentially a disk of some sort. In practice, this is only ever going to work if you have the source data on a fast SSD. So I want to know what the failure modes are like for other storage sources, and I can keep it on a network disk for getting an idea of how it handles a slow source. I want to make sure that it doesn't like block the audio thread when that happens, but I'm also not expecting it to work well unless the source is on a really fast disk. So then the disk is going to be fast. The operating system already caches blocks off the disk unless you specifically work around that. So we want to use that kind of as appropriate. And then figure out where else to do the caching. Decompressing FLAC is not that expensive, but that's one of the heavier steps that we're dealing with. But this gain scaling thing means that probably by far the heaviest step now is kind of front-loading all the decompression work and applying the window and then figuring out how to scale the resulting grain. So that step needs to be something that is pretty efficient, but we can also kind of tolerate that being the CPU bottleneck. So I don't know, just given all these architectural constraints, the thing that seems to make sense to me is to not use juice's buffering layer, to maybe use juice's FLAC layer, to maybe use juice's file layer, to not use juice's zip layer, and like write our own extremely basic like zip64 reader. But we can use juice for decompressing the compressed parts of that zip. And then as far as buffering, I think it makes sense to have a cache that stores waveform data for entire windowed grains. So it would be effectively just like a big hash table in RAM. With, you know, an eviction priority and whatever else we want, and a concurrency strategy. I guess we don't need a close up if it's grooming time. Yes, we need some kind of efficient data structure that we can use for loading and processing these grains kind of asynchronously and then accessing them in real time. That's going to have to be somewhat custom. We can use a lot of the bits and pieces that are in juice or the STL to implement that. Thinking about the kind of asynchronous strategy, that buffered stream, let's go. Let's get the documentation for that. It's one of those objects I'm always forgetting the name of because it's kind of bland, right? It's like buffered audio stream reader. Buffering audio reader. So yeah, this is one of those things that looks pretty decent from the documentation, but then if you actually go read how it's implemented, it's wildly disappointing. Buffering audio source. No, it's audio reader, not audio source. The audio source is different. Reader is like a seekable thing that comes from a file, whereas a source is like a stream source in juice terminology. Okay, buffering audio reader. Oh, the parameters. Header file is important for this too. All right, so the class that does the actual work is buffering audio reader, but that's actually private. Like it's only exposed as a subclass or like an instance of an audio format reader. So the factory for those is buffering audio format reader. That's why I'm saying I can't ever remember it, I guess. To grow. So we've got this entry point that's intended to be called on the real-time thread. Holds a lock. This does a linear scan of a list of ranges to try to figure out whether the sample is in cache. Lock is still held. We're copying. Finally unlock. And all right, we're just like spinning in this with a thread yield. If scoped unlock is weird, right? These recursive locks. Anyway, the idea here is that you either wait, the default is to block this for an unlimited amount of time. So this is the timeout case. So if there is a timeout and the timeout's passed, we're clearing the buffer and then bailing out. Otherwise, we just yield the thread and keep waiting. So I don't think the documentation was clear about this, but the default is unlimited timeout rather than zero timeout. So either it's going to wait an unlimited amount of time, or it will spin and check the millisecond counter and do that until it's out of milliseconds. And then in a separate thread, how is this keeping track of requests again? So I think this is an atomic that's shared between threads. Next read position. Oh, it's so tiny. Yeah, so this is an atomic. This is a integer where we're relying on bus level locking between stuff that might be running on different CPUs concurrently. Can we get a better view at Tuco? Brace initializers. Yeah, anyway, this would be a little more useful if we could tune the samples per block. If it had a better data structure for keeping track of blocks. But it doesn't, and not a lot in here is really applicable other than the extremely broad strategy of having a data structure that's shared between a background loading thread and the real-time audio thread. So let's see. We need a new data structure. This is when I started thinking about how the cache is keyed. What is the cache actually storing? What causes us to invalidate that stored data? And so I think it's not just going to be a cache of the data as it is on file, but it'll actually be a cache of the data we're using for each of these grains they will potentially be overlapping, but I don't know that that matters. Like, I don't know that it's really useful to have a separate cache that we manage that's caching the kind of original ranges of the file, like before we introduce the windowing, because the FLAC decompression is pretty fast and the OS has a buffer cache, and those two layers together effectively do that job. Gosh. Is this also, I think this is also really intended to read from just one place at a time. Because if we really only have a single next read position, that works if we've got one audio playback pointer. But if we're actually trying to request from two different kind of discontiguous streams of audio data in the file, then those, I mean, I guess they're not going to end up fighting over a read position, because this is assuming we only have one thread reading audio at a time. But that one audio reading thread might end up kind of bouncing back and forth synchronously with the loading thread if that, if we don't have a timeout and the data isn't in the buffer. Anyway, I'm just like thinking about how this design would apply to the situation that I've got, and that's so great. I'm probably talking too much, huh? Everybody's leaving. I'll try to shut up and describe this less and just write code and have the cute cat on the stream. Oh yeah. That was what I was up late working on. So this all kind of leads into like what do I actually need to lock down next in the design in order to implement the caching storage path here. And I need to at least have some idea of what the windowing function parameters are like if the windowing function is included in grain cache. So if the window is something that you can adjust in real time in the UI or with input from your plugin host, then I would expect that I would need to be careful about the ways in which that can invalidate the cache. And I think I thought about it enough that like that is actually going to be kind of a bottleneck, but I'm okay with it. Like if you're changing grain width continuously and just playing a bunch of different grains of different sizes. But actually that's the thing, like playing a bunch of different grains of different sizes is not really any worse than playing just different sizes of the same grain. Like what this really comes down to is what is the unique number of kind of grain and window parameters that you're accessing at once, and how many of those are you overlapping. And I think ultimately it just comes down to like how many overlapping voices are there at once. So just like kind of basic synthesizer performance issues at that point. Oh, Tuco. So I think where this leads me in designing this is I think I want window parameters that are fairly constrained, like maybe a relatively small number of parameters, and maybe they're quantized to like 127 steps or something, just to keep extremely tiny fluctuations from completely blowing my cache budget. But I think I do want to kind of spend my cache space on that stuff because that's I think a good use for it. So that led me into thinking about the window function, just like how many parameters do I need, how much variation in the parameters would be useful. And so I don't know, like if you've used any granular synthesizer before, you've probably seen some of the window settings. Sometimes they let you choose a different like mathematical function to use because there are a couple of different like window functions that give you different spectrum characteristics. A lot of that is useful for filter design or for FFTs, but less useful for granular synthesis, since here you're more just interested in like tuning the knobs and getting a good sound rather than like preserving the gain of a filter or something. So I'm more interested in just what what audio parameters would I be interested in tuning. And what I want to hear in the output from this is I want to hear that central tone that it's detecting, but I also want to hear the stuff around it. And I want to be able to adjust the relationship between those two things. So that's kind of what led me to thinking about a way to model the window as a pair of raised cosines. So you have one cosine bump that's right in the center of the grain, but you can adjust its width. And then you have another raised cosine bump, and you can adjust its width, but you can also adjust where it is relative to the other bump, and you can adjust the relative strength of the two bumps. So I was prototyping that with a Jupyter notebook. Tuco. Will Tuco complain if I close the door? There'd be less traffic noise, but I think he and I both kind of like the door open also. Experiments. That should be... I need to fix the scaling on this FFT graph, but I was trying to graph the actual window function and then the FFT and the first derivative, just to make sure those were not terrible. I might comment out the FFT until it's scaled a little better. But so yeah, I've got these two bumps in these parameters. I've just been calling them W0 and W1. You can kind of fade between them. So if this is mixing all the way to W1, then these parameters are relevant. And the width will adjust anywhere from the same width as W0 to the maximum. So at the minimum, you can still adjust it with this. This is more like a minimum width. Might need to figure out better names for these parameters, but I want something that's a relatively small number of parameters, but also not too confusing. Hopefully something that I could have sensible like mouse adjustments for. So there are places on this graph you could just drag handles to adjust it. So, and then window 1 has this phase parameter. So this would let you do some stuff that is like kind of weird on its own, but you know, I want to allow weird things. Plus, you want to be able to transition between weird nonsensical stuff and stuff that's actually really ordered. I think that's part of the interest of a granular synthesis tool is you can kind of like really mess up audio in a way that you can also like put back together in a controlled way. So, I can listen to a couple of these. That might be more like a realistic window though, right? Audio setup here could be a little smoother. Oh.
This reduction relies on process, hence it produces the thermodynamic product. Right.
These time of Scotland.
The town was the meeting place for the scientists.
Why does that sound crackly? Am I just hearing the resampling? I'm hearing glitches that I think my audio setup might be introducing. Oh. I guess this is just a browser audio element. I was used to having a download button here, but that might be a Chrome thing. Thought that was part of the widget. Anyway, we could take a closer look at that. I was looking at the spectrum in Audacity just to make sure it didn't look too terrible. I was hoping we could do that here. I just have to write some code to write a WAV file. I could also just not debug the prototype and just implement the thing. Just trying to show the spectrum of this, but the purpose of this was to convince me rather than to convince other people. Anyway, the idea here was that you'd be able to listen to kind of the emphasis between that detected tone and the kind of surround of that tone. It kind of change as you slide these cosines around. So I don't know if that actually works, but I'm hoping that as you manipulate the center window, you change how you're hearing that like very tonal part of it. But then you move this other piece around and you can kind of get more of the like ethereal like jabbering of robot voices that this will produce. I did actually want to keep that open. I think we're done modifying the prototype, but I think I'll want to at least use it for reference. Alright, and I wanted to display the window anyway because the UI has a spot for it and it looks weird with just a blank there. So that'll be convenient for just debugging all this. I want this cache. So I want to make the cache. The cache is probably a whole new set of files. I think the window is also like a subdependency of that. Oh, Tuco seems so chill. Yeah, the new database crunching tool is so little now. Yeah, like that cache might actually just be part of grain data, but about grain window. Oops. I'm frowning at how I'm already using window as both a UI. No, I'm not. Actually, I'm not talking about UI in that. It is a UI panel for a signal processing window. So at least that's consistent. What is that? Let me manually sort them. That's interesting. To go. This is currently just written to assume that this is exporting just like a flat read, like it's just passed through to the FLAC read, basically. With or without a buffer. The accessor is pretty simple right now. It takes a lock when the accessor is created. So the lifetime of the accessor is effectively the lifetime of the read lock that you take on the grain data. But the actual sample data doesn't have any of its own memory management. You're just doing a copy within that read call while the accessor is still in the stack. I'm trying to think about whether there's a simpler way to do this or whether there's any downsides, but I think I just want all the cached chunks of windowed grain data to be blobs of reference counted data in memory. You can just swap them out with new versions when they get regenerated or deleted. The actual concurrency model I'm probably going to have here is that they'll be read. I was going to say from one thread, but actually the UI might be reading the audio data too. I think I want the window graph to also visualize the waveforms of the grains that we've loaded within the window, if that's not too expensive. So it'd be nice to leave the door open for the audio data getting access directly by the UI. That's currently how the graph in the UI works. It's just got its own grain data accessor that acquires a read lock. So I'd like to continue that. I'm envisioning something where maybe the audio, like the real-time audio thread, can call something to like check out or look up a grain waveform, and the inputs to that would be the grain number, which would come from this index, and a struct with window parameters, which in practice would probably be like 4 8-bit integers or something like that. I don't know, maybe I give it more bits than that, but it'd be a collection of knobs that don't have a whole lot of resolution, but some resolution. And I think that's non-blocking, and it either just returns null immediately to say that the data isn't available yet, but in the process it's queued a request for it on the loading thread, or it goes ahead and returns a checked out copy of that grain data. And at that point, I don't know why we wouldn't just keep the data checked out until we're done with that grain entirely. The synthesizer is going to have some object that exists for the lifetime of the grain playback or the instrument playback or whatever level of detail that ends up being. And I think we can just maintain a reference to that data so that we keep it in the cache and avoid having to search for it again. Like, I don't know that there's a benefit to not keeping that reference. The grain window is also something that is in this weird space kind of between like a per grain parameter and a global parameter. Like, I think in practice it's going to be basically global, but technically it will actually be per grain, because as you're changing the parameters, you'll end up dealing with several intermediate states. I don't know how much I care about variable latency on grain playback. Oh man, I'm scaring everybody away. I really just shouldn't do C++ streams on a Saturday, huh? Maybe we should just make the cat cam as big as possible. Oh, honey. Oh, honey. Yeah. And basically coloring inside the lines with juice and using its data types whenever possible. This is like one of those cases where I'm wondering, do I even really need this? Because I don't even know if I have any juice data types inside the window. I assume I'm going to have code in there that actually generates the window, like evaluates the window function. It's going to use juice. I should probably just keep using those types. making this too complicated. Thinking about how this interacts with juice parameters and what types to make it there. I mean, I think the broad outline of this is just a struct that has a constructor that takes some floats, and then the representation has them quantized. Juice already must have some data types to do this though, right? It's like pretty funny to me when people ever suggest that their software is not political, because it feels like most of what programming is just figuring out like whose customs you must adhere to and like what kind of diplomacy to engage in between these different factions. Like, you know, when do I venture to juice for this and when do I venture to standard C++, and how do they get along at the boundaries? Quantized parameters. This is a thing, right? Juice gives you a bunch of these kind of general purpose building blocks that you will often end up using through these even higher level pieces. So like there's a value tree, which is sort of their like XML-ish kind of general purpose data type. And then built on top of that, they've got a thing that handles audio parameters. And that really, really likes floats. Like, I think they kind of mash everything into float there because that's what the interface between audio plugins and the plugin host expects. That's what we want. Really seems entirely like just a hint to the audio plugin layer rather than something that would affect how we store things. Oh man, I was like, I couldn't sleep last night because I wanted to work on this so much, and now it's like warm and Saturday, and it seems like everybody just wants to be outside instead of working on C++ code. It's tempting to make a slight diversion to actually just put these parameters into the data model for the audio processor. Just make sure that's representable easily. Maybe this is what Juice was getting at with, it seemed like a bunch of their code had a pattern which took a lock to protect accesses to an array, and then handled a pointer to an object within that array without the lock. That kind of makes sense if you hold a reference to that object and they're using reference counting. I don't know if that's what Juice was actually getting at, but I was just thinking about that because that's one strategy we could use here. Like if we're allowing references to the grain waveforms to outlive instances of the accessor, which might be the case. If we're doing that, yeah, I don't think we even need an actual hash table. I think we can just have a big array the size of number of grains that has a reference to the latest cached grain. Are we ever going to be playing multiple grains at the same time with different windows and actually want them both to be in the cache? Because if the window parameter is kind of global and we're just changing it sometimes, but we're always starting grains with one new window, then when the grain starts, it'll end up saving a reference to that waveform data and only releasing that reference when it stops playing. And so if you were just changing the window parameters a bunch and playing the same grain over and over again with different windows, you would end up caching, or not caching, but you would end up keeping all those different waveforms in memory. But they wouldn't actually end up being persistent in the cache. The cache would lose its reference as soon as that same grain was played with a different window setting. And if that actually does make sense, that makes it easier to keep the cache a predictable size, I think. It's also tempting to just say the key should be arbitrary, hashable data, and then we can figure it out later and just put it all in a big hash table. Tuco has such great hands. I was worried about this this boundary between the per note and the per grain processing. Now that I'm thinking about doing this with a grain waveform cache, this matters a lot less. Like I can So Juice has its own synthesizer class, which is intended for building a MIDI synthesizer. It's, I think, designed to support a variety of different use cases, but it maps pretty well to stuff that's like kind of FM synthesizer style, where you've got some algorithm that you're running per voice that has to generate audio blocks. And they also have examples that show you how you might have some shared sample data that you're using. I was assuming that maybe I would want to have some kind of layer that is for playback of one grain, and then have the voice kind of actually like invoke that to play grains. That doesn't seem like it would really help though, if like the voice can do the job of kind of picking and mixing the different grains if the grains are already windowed and loaded and gain adjusted and all that. So if I've got a cache where I can request windowed grains, they're loaded asynchronously into that cache, and then I can just, like, as soon as I get a reference to one of those grains that's been loaded, like the voice can continue playing, and it'll just have a reference to some pre-windowed floating point data. It can just add into its mixing buffer. Then that makes it pretty easy for the voice to handle grain repeats on its own. So instead of having to like instantiate objects of some sort for each repeated grain, I can have one voice mix together like a train of overlapping grains. Well, I guess that's basically all I had for this stream. I could continue kind of hashing out this design and playing with my cat's toes, but maybe it's good to keep Saturday's stream kind of short. Try to do this fairly frequently though. Like maybe I can get into it. Maybe I can get into a cycle of doing more frequent but less long. Also, don't know if anybody likes these software projects. I wanted to work on something that was not just like one random piece of junk that I happen to have in my garage, and software is something that is relatively easy for people to run on whatever. But, oh gosh, somebody's pressing me specifically for when is the next stream. That's a good question. Maybe I could do one tomorrow, maybe Monday. I have not been setting a specific time for these yet, sorry. Oh, Took. My strategy for this is mostly to have a project I can kind of putter with continuously and do some portion of that work on stream, and then some portion of it I can do kind of behind the scenes. And that's mostly just because I find that if I try to do like every ounce of it on the stream, that gets really, really tedious really fast. Well, I'm glad some folks enjoy the rambling about the thought process. And yeah, I'll try to keep this from dragging on, but keep things coming frequently, and keep Tuco well fed. He was really, really intense about food the other day. I just ran out of the stuff that he likes the most, and I have some more of it that is taking a couple days longer to get here than I expected. And I was thinking that I could just feed him one of the many other foods that I have in the meantime, but he is being really intense about it, and so I ended up getting the food that he wanted, and now he's chilled out about it a lot. All right, I'll see you next time, folks.